Doctor, we can't hear you. Dr. Hanif?
Can you hear to my presentation now?
Yes, yes.
Okay,
But the
sorry.
first two slides we couldn't hear.
Sorry for that.
Doctor, is this lecture recorded?
Yes, I'm
Okay.
recording it now.
Yes, thank you.
Okay, sorry for that technical problem. So I did mute my microphone. Sorry for that. Okay, good morning, everybody. Very good day. So we're going to start with our presentation, lecture 7, which is a new chapter. So the topics for today will be on Fourier series, yeah, and also signal spectrum. Okay, thank you, Ling Jingkai, yeah, for your message. Right. Okay. So this will be the topics for today, in which we're going to cover about the trigonometric and exponential type of Fourier series. Okay, I'm not sure whether you have learned about these topics before in mathematics. So have you learned about these topics of Fourier series before in mathematics?
Yes, doctor. Math
Oh,
1.
okay. So when is it? Is it during your first year?
Math 1, yeah, the first semester.
First
In
semester.
differential equation, we had some like knowledge about it. Not like Math 1, but
Oh, okay. Okay, good to hear that. Good to hear that. Yeah. Okay then. So there are a few topics in Fourier series. You can see based on the CI. You're going to have trigonometric and exponential type of Fourier series. We also have the topics of average value signals theorem, which is Parseval's theorem. And finally, we're going to cover about the application of Fourier series in electrical circuit. Not that much in terms of its content, but hopefully it's enough for you to understand about the G's, yeah, the importance of Fourier series, and also the use, yeah, the application of it, particularly in the field of electrical engineering. Yeah. Okay. Good. Right. Okay. So why we need to consider, or why we need to learn about the Fourier series? Okay, so basically, Fourier series is used to express a complicated periodic signal. Okay, as a sum of simple signal, which is a sinusoidal signal. So I believe that most of us are quite familiar, yeah, quite familiar with a sinusoidal signal. Okay, sinus, cosinus. Yeah, we have learned this even from our secondary schools. Yeah. Okay, so what actually done by Mr. Fourier? Yeah, Mr. Fourier is the inventor of this Fourier series. Is that he used this sinusoidal signal as a mean to express a complicated periodic signal. Yeah. So the important words to be considered here is a periodic signal. Yeah. Okay. So which means that Fourier series is a mathematical series which is actually represent any form or any type of periodic signal. Yeah, any type of periodic signal. It doesn't matter what shape of this periodic signal. It can be square wave, it can be triangular wave, it can be sawtooth wave, as long as it is periodic. Yeah. So these signals can be represented by a sum of sinusoidal signal. Okay. Right. Yeah. So hopefully you are clear about this explanation. Okay. In which any form of complicated periodic signals can be represented by a sum of sinusoidal signal. Okay, because in sinusoidal signal analysis is much easier. Okay, so this mathematical series basically used widely for instance, in the field of electrical engineering. So we're going to see this in the application side of this lecture. Okay. And then we also use it in the field of image processing. Okay, image processing and also optics. So it's varieties of application will be applying this kind of mathematical series, yeah, of Fourier. Right. So, but the important part here is that you must understand that the Fourier series is a series used to represent any periodic signals, any type of periodic signals in the form of sinusoidal signals. Yeah. Okay. So hopefully you're clear about this. Okay. So why we need to consider a periodic signal? So basically, if we, I'm not sure whether you have entered the lab or not, yeah, the electrical engineering lab, but knowing that now it's a pandemic situation, so the lab is closed, okay, and even the lab session is on, but it is just a simulation-based lab, yeah. So you don't have, you're not having a feel of touching the equipments in the laboratory. So very sad to hear this kind of problems, yeah. Okay, so basically, if you have a chance to enter the lab, you're going to see a lot of equipments in the lab, which include the oxidators, function generators. So this kind of equipments, if you can, basically will generate the kind of signals. It include the square wave, triangular wave, sawtooth wave, sinusoidal wave. Yeah. I can see that this is a common signals which can be generated in the lab. Yeah, in the lab of electrical engineering. Okay. But in most of the situation that we have in a real world application, okay, the signals that we are going to have, most of them are non-sinusoidal. Yeah, non-sinusoidal. Okay. For instance, our voice, okay, is not a non-sinusoidal signal. Okay. So this kind of signals which are not sinusoidal, so it's quite difficult to analyze. Yeah, we are having difficulties in analyzing this kind of signals. So that is why I mentioned to you before that if we can represent this kind of signals which are periodic but not sinusoidal, so if we can represent them in terms of sinusoidal form, so analysis will be much easier. Yeah. So that's what I meant by the importance of Fourier series before. Yeah. Okay then. So this I give you the examples here that you want to actually relate the sinusoidal signals with the periodic nature of the signals. Yeah. Okay. So for instance, if we have these YT functions, where we have a combination, a summation of a few sine wave, which we have sine omega naught t, 1 over 3 sine 3 omega naught t plus 1 over 5 sine 5 omega naught t, and so on, okay, in which the signals term can be represented by this general value, yeah, in which the value of n can be extended from 0 to infinite. So we have a summation of those sine wave signal. Okay, so what we're going to do now is that we are trying to add those terms. Sorry, we are going to add those terms here in these equations. Yeah. Okay, so for the first terms, which is sine omega naught t, we are having these very nice sinusoidal functions. Yeah. Okay. So for the second case is that I want to add the first term and the second term. So if I add those terms, I'm going to have this. Going to have this, which is a summation of the first and the second term. So it's very nice signals, but now the sinusoidal function is said to be distorted. Yeah, it's said to be distorted, so we cannot get Very nice sinusoidal wave, very smooth sinusoidal wave, but we have a distortion at the peak and the lower peak of this wave. Yeah. And further on, if I add another functions, another terms, which is a 1 over 5 sine phi omega naught t, we can notice that the addition of those terms will result in these signals. Yeah, so we can see that now uh, the peak and lower peak are becoming more distorted, and we can see that the slope, of this sinusoidal wave is said to be more steep, yeah, going to be more steep, and it is actually approaching a straight line, yeah, approaching a straight line. So these are the two things that we can note, yeah, we can notice from this addition of the signals. So as the term increase, we can notice two things. The first one is that the peak and lower peak are said to be more distorted, and the slope of the wave is said to be steeper, and it's approaching a straight line. Yeah. Okay. Further on, if we add it with more terms, so we have addition for the fourth terms and addition of the fifth term. So what I meant before is true. Yeah. So we can see that the peak and low peak is becoming more distorted, and the slope is becoming uh, more towards a straight line configuration. Okay, so we can imagine that if we add further of these particular terms of sinusoidal terms, yeah, it's up to 5 only. So if we add more terms up to infinite, what can we deduce from these findings actually? So we can see that these particular signals will be approaching a signals which looks like a rectangular signal or periodic rectangular signal. Am I right? Yeah, we're going to have a periodic rectangular signals in which we can see that a distortion here somehow will be a straight line. Yeah, be a straight line for the both a peak and lower peak. Yeah, we have a straight line, and also this slope will then become will be a straight line also. So all the slopes will be a straight line. So you can see that based on these examples I showed to you, that the rectangular pulses or rectangular signals, which is periodic, can be actually represented by a series of mathematical terms in a form of sinusoidal functions. Okay, so this is actually a proof that any periodic signals can be represented by a series of sinusoidal signals. So this is what we call as a Fourier series. Okay, so is that clear on this? Hello?
Clear, Doctor.
Oh,
Clear,
okay.
clear, clear, doctor.
Okay. I thought you were sleeping. Sorry,
No,
sorry.
it takes time to open the mic. Sorry.
Oh, okay then. Hopefully you are clear about this. Yeah. So basically, what I want to show you here is that the examples that the periodic signals in this case is rectangular functions can be actually represented or can be actually represented by a series of sinusoidal signals. So you can have the same proof for another periodic signals, for instance, a triangular functions, a sawtooth function, or any periodic signals. Yeah? So you can prove this on your own later on. Yeah. Okay, good to hear that. So okay, let us proceed further. Okay, now I'm going to introduce you to a topics of signal spectrum because this topic is very much related to the Fourier series topics. Yeah. Okay then. Uh, Okay then, what is meant by signal spectrum? So a spectrum is basically a way, a method in which we can represent a product signal, which is basically initially in a time domain, yeah, in a form of frequency domain. Okay, so from here we can now say that any signal in a real world environment can be represented in two domains. We can have it number one in a time domain and number two in frequency domain. Okay, so basically in a frequency domain, if you want to represent the periodic signal, we need to use a signal spectrum, in which the signal spectrum consists of two types of spectrum, which are the amplitude spectrum, is the first spectrum, amplitude spectrum, and the second one is a phase spectrum, in which the amplitude and the phase spectrum are used to represent the amplitude and the phase of these periodic signals, uh, yeah, of this periodic signal. So it means that the spectrum basically is used to represent the amplitude and the phase of these periodic signal. Okay, let's have a look at these examples here. Okay, in which we have the use of AM modulator. Okay, so AM modulator basically used in communication, yeah, in which you want to modulate the signals. Okay, so you're going to learn this in SEE 3533, Principle of Communication later on in third year semester one, in which this is a way, a method on how we can transmit the signals further away, yeah, further away. Right. So in AM modulation, we need to use two types of signals. We have a carrier signals, FC, okay, the frequency is FC, and you have the information signal, which is represented by the FM. Okay, so by the AM modulation, okay, so when these two signals will be modulated or will be added, yeah, will be added, and we're going to have in time domain, the signal will behave or looks like this. Okay, this is a signals in time domain for the AM modulation. Yeah, AM modulation. So from these signals here, we know that the signals which are having the AM modulation is said to have these characteristics of a time domain signals. Yeah, there's an envelope of the signals. Yeah, there's a peak and there's a lower peak of the signals. So, but in electrical engineering, we are more interested to know what is or what are the frequencies component exists in this AM signal. Yeah, what are the frequencies exist in this AM signal? So for this, we need to have the signal spectrum. Yeah, need to have a signal spectrum, and for this, we can have two spectrums plot, which are the amplitude spectrum and the phase spectrum. So what we have here is the amplitude spectrum, in which from this particular signal, we're going to have three lines, which shows the existence of three distinct frequencies of the signals, which are the FC. Yeah, FC is what? FC is your carrier signal. Then we have the FC plus FM, which is the addition of the FC and the FM. Another one is FC minus FM, which is the subtraction of these two frequencies. So in AM modulation, we call this as a carrier frequencies. These two bands here are called side bands. Yeah, side bands. Okay, so from these time domain functions from these signals, AM signals in time domain, we can have the spectrum of the signals, which shows the component of the frequencies that exist in this AM signal. Okay, so I hope you are clear about the importance of the use of the signal spectrum, which is actually, in a simple word, the spectrum, the signal spectrum is used to represent the time domain signal in its frequency components. Yeah, frequency components. So hopefully you're clear about this. Yeah. Okay. So for this spectrum, basically there are two types of spectrum. Two types of spectrum. So we're going to cover that one by one. The first type of spectrum is what we call as one-sided spectrum. Yeah, one-sided spectrum in which the signal of one-sided spectrum is a trigonometric representation. Yeah, means that the signals which is actually represented by this one-sided spectrum, the equation of the signal is in a form of trigonometric terms. Yeah, for instance, yt, okay, this is your signal yt. It is equals to 1 plus 1.2 cosine omega naught t plus 30 degrees plus 3 cosine 2 omega naught t minus 45 degrees. So this is a sample of a signal which can be represented by one-sided spectrum because why? Because the yt is in a form of trigonometric terms. Yeah, trigonometric terms. So if yt is in a trigonometric term, so it must be represented by one-sided spectrum. So how to sketch the one-sided spectrum? So let us learn how to sketch the spectrum. Yeah. Okay. So what we have here on left-hand side is your amplitude spectrum, and what we have here on the right-hand side is the phase spectrum. Okay. So for the amplitude spectrum, yeah. Okay. So if we base on the equations here, we can note that there are three components. Yeah, we have one. Yeah, we have 1.2 cosine omega naught t plus 30 degrees. We have 3 cosine 2 omega t minus 45 degrees. Okay, so one here is considered to be a DC component. A DC component. Why DC component? Because it does not have any frequencies value related to it. So since there is no frequencies value related to 1, so 1 is considered to be a DC value or DC amplitude. Okay, so for 1, we can simply draw an arrow, one arrow, which is the amplitude of 1. Okay, so basically there are two axes. The horizontal axis is omega, which represent the frequency component, and the vertical axis is y, which is the amplitude of the signals. Yeah, so we use y capital to represent the amplitude of the signals. Yeah. Okay, so back to this amplitude just now. 1 is a DC value, so we have the amplitude of 1 here. For second terms, the amplitude value is equals to this, which is 1.2. And this amplitude is related to a frequency component of omega naught. So that's why we have here, at the frequency of omega naught, the amplitude is 1.2. So this is what we call as the first harmonic. Yeah, the first harmonic, because the frequencies is omega naught. And for the third term, the frequency is 2 omega naught and the amplitude is 3. So we can see that for this component at frequency of 2 omega naught, we can have the amplitude of 3. So this is your amplitude spectrum for these YT signals. Okay, so note that the spectrum is only on one side, on the positive side only. Yeah, positive side only. That's why the name of this spectrum is one-sided. Yeah. Next, let's have a look at the phase spectrum. Okay, for the phase spectrum, the horizontal axis will be a frequency component, a frequency value, and the phase the vertical axis is the phase. So the phase can be in degrees or it can be in radian. Yeah, it can be in degrees or it can be in radian. So this example we use a radian, so you can use degrees also, no problem. Okay, so let's have a look on the plotting of this phase spectrum. So we know that for a DC component, there should be no frequencies, there should be no phase involved. So there should be no phase for a DC value, yeah, which is at omega equal to 0. For omega naught, the phase is 30 degrees or pi over 6 radian. So we have for omega naught, the phase is pi over 6. And for 2 omega naught, the phase is negative pi over 4 in radian unit. Yeah. Okay. So hopefully you are clear about this. Yeah. So note that the range for the phase will be from negative pi to positive pi, or from negative 180 degrees to positive 180 degrees. Yeah. Okay. So this is a one-sided spectrum. Any question for one-sided spectrum? if there's no questions, let us proceed with the second type of spectrum, which is a two-sided spectrum. Okay, so the two-sided spectrum basically is related, yeah, related to a represent.
Doctor?
Yes, yes.
Doctor. So I can go back for the first slide. The slide prior to this one, the previous slide.
Let me see here. This one.
Yes.
Okay.
In the phase diagram, uh, is the amplitude fixed?
For the phase, for the right hand side here, right?
Yes.
Okay.
Is the amplitude, because I don't see the changes between the two amplitudes.
Oh, okay.
Uh,
All right. So basically, the amplitude will represent this angle value. So basically, if you base on this, the height of negative pi over 4 should be bigger, should be larger, yeah, as compared to the height for the pi over 6.
so in the phase diagram, the number 1.2 and the number 3 are irrelevant, right?
Yes, correct. Because this is just a representation of the face only. This will
Yes.
be a representation of the amplitude.
Yeah, and the amplitude, the phase will in the amplitude diagram will be irrelevant. Thank you, doctor.
Okay, right. Okay, so back to this slide, which is a representation of a complex exponential type of Fourier series. So we're going to see this later on, yeah, on the Fourier series type. But for the time being, we just agree that if we have a signal, product signal, which is in a form of complex exponential, so it can be represented by a two-sided spectrum, yeah? Okay, so for two-sided spectrum, basically, we're going to represent it by these complex exponential terms, okay, in which if we refer back to the previous equation still, we have yt equals to 1 plus the same terms as before. So what I did here is that I'm now transforming all the cost terms here into a complex exponential by using what we call as Euler's representation. Yeah, we have learned this in chapter 1 before. Euler's representation, which is a representation of cosine function in the terms of complex exponential. So by using this Euler's representation, those cosine terms, the second and the third terms, can be represented by these equations, yeah, by these equations here. So we can notice here that from 3 terms before in a trigonometric, we can have 5 terms in a complex exponential. Yeah, we have, there should be no changes for a DC component, but for the second component, it is now consists of 2 different components. Okay, we have a components at positive omega naught, with a phase of pi over 6, and we can also have a component at the negative omega naught frequency and the phase of negative pi over 6. Okay, the same things applied for the third terms here. From a single terms in cosine, we can have it as a positive 2 omega naught terms with a phase of negative pi over 4. And also we can have a negative 2 omega naught terms with a positive pi over 4 phase. Okay, so I hope that you understand how to transform from a cosine terms to a complex exponential. So this is something that you have to understand. Okay, so from these terms, which consist of complex exponential, we can then use them to plot the spectrum. Okay, so for left hand side is your amplitude spectrum, right hand side is your phase spectrum. So let's have a look at the amplitude spectrum. So again, horizontal will be the frequencies component or frequency axis. Vertical will be the amplitude, represented by Y capital. Okay, so we are supposed to have 5 arrows, supposedly, because we have 5 terms here. Okay, so the C value is still there, we have 1. The second term here we have at frequency positive omega naught, the amplitude is 0.6. Okay. The third terms, we have frequencies of negative omega naught. The amplitude is 0.6, so we have it here, yeah, negative omega naught, which is the amplitude. For the third term, sorry, for the fourth terms, we have at positive 2 omega naught, the amplitude is 104.5, this is the 1. And at negative 2 omega naught, we also have the amplitude of 1.5. So it is now becomes a two-sided spectrum, which cater for the positive frequencies and the negative frequencies, yeah? Okay, this is just a matter of representation. We cannot have a negative frequencies, yeah? But as a matter of representation, because the equations that we have is in a complex exponential, so we need to have as shown here, as shown here, yeah? All right. So in terms of the phase spectrum, okay, the same horizontal axis, which is the frequencies, and the vertical is the phase. So let's have a look on the plotting of the phase spectrum. For omega naught frequencies, the phase is pi over 6. So we can have it here. Omega naught frequencies, this is the phase. Then we have a negative omega naught. The phase is negative pi over 6. Okay, please note that it's not positive. It should be negative pi over 6. So we have it here. That should be the phase for negative omega naught. And then we have for 2 omega naught positive, the phase is negative pi over 4. And finally, for negative 2 omega naught, the phase is positive pi over 4. Okay, so that should be the plotting or sketching of the phase spectrum and the amplitude spectrum for these equations of yt, which have been written in terms of complex exponential terms. Okay, so I hope you are now understand clearly on the difference between one-sided spectrum and two-sided spectrum, okay, and the equations which govern, yeah, which govern the use of whether to apply one-sided or two-sided spectrum. Okay, right. So let's have a look at this example before we proceed with the next slide. Yeah. So we are given here in this example the amplitude and the phase spectrum for a signal of yt in which we are having it as in the form of two-sided spectrum. Yeah. So if you can look based on this diagram, this is a two-sided spectrum. Yeah. So we have these frequency components for the signals, which is located at pi. So we have frequency component of pi and we have frequency component of 5 pi over 3. Okay, so based on these spectrums given, number one, you have to obtain the complex exponential Fourier series for yt. Okay, complex exponential Fourier series for yt. And the second one is you need to obtain the trigonometric cosine Fourier series for yt. Okay, so these are the things that you have to obtain, yeah, based on this diagram. So let's have a look on the solutions for this example. Okay. So can you see the solutions clearly? Can you see the solutions clearly here?
Yes.
Okay, good. Thank you very much. Right. So this is solutions for the examples that we have just now. So I repeat it here. Yeah, I re-sketch the diagram of those signals. Okay. So we know that based on this diagram, it should be written in terms of complex exponential for this particular signal. So basically, we can write it as follows. We have 3 DC value. Okay. So I start from this left-hand side, 0.5 exponential negative j pi 5 pi over 3. So since we don't have any phase value, so there is no phase related to these frequencies of 5 pi over 3. Okay, there is no phase here. So we just let the equations to be just consist of the amplitude value, 0.5 with these frequencies value, 5 pi over 3 negative. Then we have for the second frequencies component, which is negative pi, so it should be 1 exponential negative j pi t, and we know that from the phase spectrum, the phase is 3 pi over 2, so it should be exponential j 3 pi over 2. Okay, then we have for frequencies of pi, the amplitude is 1, the phase is negative 3 pi over 2, so we have exponential j pi t, and the phase exponential negative j 3 pi over 2. Okay, and for this 5 pi over 3, we have the amplitude of 0.5 without phase. So you have 0.5 exponential j 5 pi over 3 t. Okay, so this is the method on how we can extract the information from these spectrums in the form of equations, yeah? In the form of equations. So this is the equations that relates the spectrum components just now, yeah? Hopefully you understand about this. So once you have this, we can proceed further with these solutions of these equations. So we have further on 0.5 exponential negative j 5 pi over 3. So we can combine these together. So we have these terms. So we have these terms and we have these terms here. So what we shall do now, okay, so this is the answer, yeah? This is the answer for part 1 of the question, which is yt in terms of complex exponential. So yt that we have here is in terms of complex exponential. So we are now trying to answer the second part, which is to write the yt in terms of trigonometric cosine. So to use to write the yt in terms of trigonometric cosine, we need to use an Euler's relationship, yeah, where we have cosine theta is ej theta plus exponential negative j theta divided by 2. Okay, so we need to apply this Euler's relationship to these terms that having same frequencies value, which are 0.5 of negative j 5 pi over 3t and 0.5 exponential positive j 5 pi over 3t, and also these terms of negative j pi t and these terms of positive j pi t terms, yeah? So we need to combine them together. So we are having these combinations, okay? 3 plus 0.5, we combine them, plus exponential of these terms, we combine them together, and we are supposed to get these equations here. Okay, all right, so you are having finally 3 plus cosine 5 pi over 3t plus 2 cosine 5t, 2 cos pi t minus 3 pi over 2. So this is yt in terms of trigonometric cosine. Okay, any question for this example? It's a very simple example which actually we want you to understand how to transform from the spectrum into the equations. Hopefully you are clear about this, yeah? Okay, so let's go back to the lecture. Okay. Right, so once you have understand the spectrum of the signals or signal spectrum or representation of the spectrum, we are now ready to start our lectures on type of Fourier series. Okay, types of Fourier series. So I believe that since you have learned Fourier series before in mathematics, yeah, so you know that there should be three types of Fourier series representation. Yeah, three types of Fourier series representation. The first type is shown here. Where the Vt, which is Vt is your Fourier series equation, can be represented by a series of sinus and cosinus terms. So as shown here in the slide, the Vt is represented by a summation or a series of signals or equations in terms of cosine function and in terms of sinusoidal function. So this is the first method, the first way of representing the equations or representing the Fourier series, in which the above term can be simplified further in this form of Fourier, series. We have Vt is A naught plus summation An cos n omega naught t plus summation Bn sin n omega naught t, where An and Bn are the Fourier coefficients. So I believe that you have seen these equations before, yeah, in mathematics. Okay, in which all these Fourier coefficients A naught, An, and Bn can be actually written in this equation or represented by this equation, 1 over t of the integrations for the Vt, cosine and sine, yeah, for An and Bn respectively, where t here stands for the signals period, yeah, or period of the signals, yeah. Okay, but don't worry on this integration, because for this course we are not going to test you on the integration. Means we are not going to ask you to find what should be the A naught, what should be the An, and what should be the Bn from the integration approach. Yeah, so we're not going to test you on the integrations. Yeah, so don't worry about this. But I have to put this in this slide because this is the fundamentals of Fourier series that need to be understood. Okay. Okay, so this is second types of Fourier series, which we call this as alternative type of trigonometric form. Okay, in which the Fourier series is represented by Vt, previously is Vt of A naught, An, and Bn. So we can also write this Vt in terms of uh, cosinus, yeah, cosinus terms only. Previously, we have cosinus and sinus, but for the alternative form, this sinus form can be actually transformed into cosinus terms only by this form, yeah, by this method, in which the Vt is A naught plus summation from n equals to 1 to infinite An cos n omega naught t plus theta n. Okay, so now we can see that the transformation from the first type to this second type is that although we ignore or although we cancel the sinus wave for the second type, but there should be addition of the phase here. Addition of the phase, and there should be also a modifications on the amplitude of the terms, yeah, in which the amplitude of this An is basically obtained from the square root of the An squared plus the Bn squared. Okay, we can notice it from here that, for instance, if we consider n equals to 1, yeah, n equals to 1, so we are supposed to have A1 here and we're supposed to B1 here, right? So in the form of alternative form, or in the second form of Fourier series, the A capital 1 is equals to square root of A1 squared plus B1 squared. Okay, so this amplitude of the new form, or the amplitude of the alternative form or second type of Fourier series basically can be obtained by a square root of this An squared and the Bn squared, and it should be depending on the value of n. Yeah, depending on the value of n. Yeah. Okay, and for the phase value, the theta n can be calculated by simply use an arctangent of negative Bn over the An. Okay, so if we refer back to the previous examples where we use n equals to 1, so the theta 1 should be arctangent of negative B1 over A1. Okay, so the same things apply for other values of n. Okay, so I did just now is just for the value of n equals to 1, in which by substituting the A1 and B1 in both equations here, we can calculate the new amplitude and the new phase for these terms. Okay then, so hopefully you understand about this second type of Fourier series. So you can prove this on your own, means that migration from the first type to the second type, because both are interrelated. Yeah, you can prove this on your own, but it won't be tested. It won't be tested. Yeah, so just for your understanding on this migration, yeah, from the first to the second type of Fourier series. Okay, hopefully you understand about this, yeah. And one more thing is that if you can recall back, if you can refer to my Google Classroom entry for this week lectures, I did give you the appendix or the attachment, yeah, the attachment for the Fourier series. You can refer to Google Classroom. So in the attachment, I did, basically that will be the attachment that will be provided to you in your tests and also in your examinations. So you don't have to memorize those attachments. So it will be provided to you. Okay, and if you refer to the attachment, there are formulations, yeah, formulations of the.
第一个啊，没有聊，
Hello.
我确认好，
Hello.
没有哦，等一下就没有了。你要确保上来，都是黑包。黑包。
Okay, so I think you have mistakenly switched on the microphone, yeah? Okay, then. Okay. Okay, so if you refer to the attachment in the first page, yeah, on the first page, you can see that there's a table. There's a table where we have a table which consists the explanation about the type of Fourier series, where the first table or the first row is for the first type of Fourier series, the second row is the second type of Fourier series, and the third row is for the complex exponential type of Fourier series. You can refer to that table, yeah, or this equation. So everything will be given to you, and you don't have to memorize these formulations, yeah. Okay, so let's have a look at these examples here, in which in these examples you have to calculate or you have to obtain the Fourier coefficients, yeah, Fourier coefficients for the given periodic signals, and following that you need to plot the magnitude and the phase spectrum for these signals, yeah. Okay, so let's have a look on the first examples here, where we have 1 plus sine omega naught t plus 2 cosine omega naught t, okay, plus cosine 2 omega naught t plus pi over 4. Okay, so let's have a look on these solutions, yeah. Right. Okay, so this is solutions for that example. You are given these equations of xt, which is 1 sine omega naught t plus 2 cos omega naught t plus cosine 2 omega naught t plus pi over 4. So we are not sure whether this equation xt, is it first type or second type? Because for the first type, we are supposed to have only cosine and sine without phase terms, right? And for the second type of Fourier series, it must be in a cosine terms without a sine terms there. Yeah, I repeat again. For the first type of Fourier series, it must be a combination of cosine function and sine function without any phase component, supposedly. And for the second type of Fourier series, it must be only, yeah, it must be consist only a cosine terms without the sine terms there. So basically what we have here is a combination, yeah, combination of terms which consists of cosine and sine, yeah. So we need to actually transform this xt in a second types of Fourier series, because if you want to represent this xt in terms of a one-sided spectrum, if you can recall back to what we have learned previously, if you want to sketch xt in terms of one-sided spectrum, xt must be in terms of cosine trigonometric terms only. Yeah, cosine terms only. So we need to actually transform this sine function into cosine function. So how to do this? So this is where we need to apply the equations that we have learned from the previous slide. Okay, so if we base on these two terms here, both of them are related to the same frequency components, where we have omega naught and this omega naught. Okay, and Based on this, we can see that A1 shall be equals to 2. Okay, the amplitude is 2, which is for the A1. For the B1, the amplitude is equals to 1. So what is A1 and B1? Basically, this is the representation of AN and BN. Yeah, representation of AN and BN, which for the first type of Fourier series. And since we have the frequencies is omega naught, so we can see that n equals to 1. So that's why we have A1 and B1 here, right? Okay, so from A1 and B1, which has been identified, we can straight away calculate this new magnitude value and the phase value, correct? The amplitude value and the phase value. So we have A1, okay, is a square root of A1 squared plus B1 squared. So we have set of 5. While for T1, it should be arctangent of negative 1 over 2, which is arctangent of negative B1 over A1. So we have negative 1 over 2, and the angle for this will be negative 26.57 degrees. Okay, so this is your amplitude and the phase for combination of sine omega naught t and 2 cos omega naught t. And following this, we can rewrite the xt in terms of this equation, where we have 1 plus, okay, so this is combination of these two terms. So we have set of 5 cosine omega naught t minus 26.57 plus, okay, cosine of 2 omega naught t plus pi over 4. There should be no changes to that terms. Yeah, so that is your xt, which is obtained from the first or from the original terms here. So now will be the equation of xt, which can be used to sketch the spectrum. Okay, any question for this example before you proceed further?
Yes, Doctor.
Okay. Yeah, okay.
For changing from sine,
I can't hear you.
for changing from the sine to cosine,
Correct.
we can just like add an angle of negative 90 and change it to cosine, right?
Correct.
So is it making a difference or?
Okay, so correct that you can use cosine omega t minus 90 into
Minus
the sine
90
omega
degree,
t,
yeah.
correct? But how you want to combine this and this? I want you to combine cos
We
omega
can
t.
just sketch it alone.
Okay.
Like we can sketch it alone. Like it
Okay.
will be four.
It's up
It
to
will
you.
be four.
So you can use the harder way or you can use a simpler way. Okay, so as long as you can find the answers, that should be okay. As long as it's correct. So there's so many methods. Yeah, there are 2 or 3 methods to transform from sine to cosine. But what I did here is I think the easier way to be done. Yeah.
Okay, okay, okay.
Okay.
Thank you.
Good. Welcome. Any more questions, guys? Hopefully you understand. Okay. Hopefully by this you understand how to convert. If we have 2 components or 2 terms which consist of sine and cosine having the same frequency, we want to convert these 2 into a single cosine term. So this is the way, yeah, of transforming into a single cosine term. Yeah, hope you understand. So from now, since you have all of them consist of cosine terms only, so straight away we can sketch the spectrum, which is a one-sided spectrum, as what we have learned in the very early part of this lecture. So we have 1 as the amplitude. So this is the amplitude, yeah, and this is the phase, the frequencies. So 1 as the amplitude is 1, and omega naught frequency we have set of 5 for the amplitude, and 2 omega naught we have the amplitude of 1. Okay, so that should be the amplitude spectrum for xt. And for the phase, okay, for the phase we can have 2 phases here. The first is for omega naught t, which is negative 26.57. So we have this is the phase for omega naught frequency, while for 2 omega naught frequency the phase is 45 degrees. So we can have it here. Okay, so that should be the spectrum, both the amplitude and phase for this xt signal. Okay, then hopefully you understand about this example. Okay, so let's have a look at the second example. I think you don't have to refer back to this slide of lecture 7. So straight away you just use this solutions slide. So we are given this yt. Okay, yt is 10 plus 3 cos omega naught t plus 5 cos 2 omega naught t plus 30 plus 4 sine 3 omega naught t. Okay, so if you base on this yt, we have 4 terms with different frequencies value. 10 is a DC value, no frequencies component. This is for omega naught frequency. This is for 2 omega naught frequencies. This is for 3 omega naught frequencies. Okay, this is actually related to the question asked by your friend just now. Okay, because based on this, we don't have any other component that have 3 omega naught frequencies, right? We only have a single component of 3 omega naught frequency, which is sine component. We don't have any cosine component with 3 omega naught frequency. So based on this, we can straight away use identity. In which identity can be used to transform this sine into cosine term straight away, where we have 4 cosine of 3 omega naught t minus 90. Right? So we can straight away convert it into, by using identity, we can convert it using, we can convert sine into cosine by using the trigonometric identity straight away. Okay, now we can say that all the y terms here consist only cosine terms. So straight away, we can sketch a single-sided spectrum. Okay, so we can have 2 spectrums. The amplitude spectrums here, where we have 10 as DC value, 3 the amplitude for omega naught frequencies, 5 the amplitude for 2 omega naught frequencies, and 4 the amplitude of 3 omega naught frequencies. While for the phase will start at 2 omega naught because no phase for omega naught. So at 2 omega naught, the phase is 30 degrees, while for the 3 omega naught, the phase is negative 90 degrees. Okay, so that's how we sketch the spectrum for these equations of yt. Okay then, any questions up to this example? No? Sorry. Okay. Right, so this is another example here. We are given a signal Vt equals to 10 plus summation of n from negative infinite to positive infinite with n not equals to 0. Okay, and the terms is j 1 above n pi exponential j n pi t. Okay. We need to express the trigonometric cosine form of Fourier series for Vt up to the second harmonics. Okay, so we are given here initially, we are given the Vt in terms of complex exponential terms, right? But the question asks us to express the Vt in terms of trigonometric cosine form. Up to second harmonics means that up to n equals to 2. Yeah, up to n equals to 2 is for second harmonics. Okay, so hopefully you understand what is actually requested by this question. Okay, so let's have a look on the solution for these questions. Okay, so we are given these questions just now, Vt of 10 plus summation of this. So what we have to do now is that we have to expand. Yeah, we need to expand this Vt from n equals to negative 2 up to n equals to 2. Okay, so we have to expand this Vt terms. Yeah, so when we expand it from negative 2 to positive 2, we are supposed to get these terms, a summation of terms. Yeah, we have 10, the DC value. So what we have here is for n equals to negative 2 value. Okay, the second term here is for n equals to negative 1, in which we obtain this by just substituting respective n value. Yeah, by substituting negative 2, you're going to get this. By substituting negative 1, you're going to have this. And the same things applied for n equals to 1, and n equals to 2. Okay, so what we're going to do now, once we have expanded these terms, we need to combine them accordingly. We need to combine them, is that we have to combine the respective frequencies component. Let's say we have 2 pi with negative 2 pi, and also positive pi and negative pi. So we need to combine them together, because why? Because we want to apply the Euler's relationship, because we want to convert this complex exponential into trigonometric cosine term. So we need to apply the Euler's relationship. So now let's proceed with that. Okay. One thing to note here is that the j terms here, so we have j terms for both second and third terms. So j terms basically can be written as exponential of j pi over 2. Okay. And negative j term is exponential negative j pi over 2. So you can expand this on your own. Yeah, because ej pi 2 is cos pi 2 plus j sine pi 2. Yeah, so by expanding this term, you're going to find out that j basically is equals to these terms. Yeah. Okay, so we're going to substitute j, this j and negative j into these equations here. So you're going to have these equations of Vt. So Vt now will consist of phase component. Yeah, will consist of phase component. So the second terms now becomes plus pi over 2. The third terms now becomes negative pi over 2. Okay, and the same things applied for the fourth and the fifth terms. Yeah, so you can have a look, you can try this on your own. Yeah, in which by substituting j equals to exponential j pi over 2, so all the terms here will be now having their phase value. Yeah. Okay then, so we can now apply the Euler's relationship for these exponential and these exponential terms. So we're going to have finally 1 over pi cosine 2 pi t plus pi over 2 and 2 over pi cosine pi t plus pi over 2. So this is a transformation from complex exponential to trigonometric cosine terms. Okay, so now we have the Vt functions in terms of trigonometric cosine, which have answered the question just now. Okay, hopefully you are clear about this. Yeah. So from here, if you want to sketch the spectrum, you can sketch this on your own, in which we are supposed to get one-sided spectrum with respective amplitude and phase values. Yeah. Okay, any question for this example? No? Okay, if there's no question, let us proceed with more examples here. Okay, so basically these examples given is to ensure that you really understand relationship between the Fourier series equation, yeah, in this case in trigonometric terms, okay, and how to sketch those Fourier systems in its spectrum representation. Yeah. So basically, this is what the purpose of these examples is all about. Yeah. Okay. So from these examples, we are given two signals, f1t and f2t, in terms of their spectrums. Yeah, in terms of the spectrum. So left hand side here is a spectrum, the amplitude and phase for f1t. Right hand side here, this first and second is the amplitude and phase spectrum for f2t. Okay, this is for f1t. The spectrum here is for f2t. Both are single-sided, yeah, or one-sided spectrum. The question now is, you need to sketch the f1t and the f2t signals in time domain representation, yeah. Yeah, we need to sketch the f1t and f2t in time domain representation. Number two, we need to write the trigonometric Fourier series for ft, which is a summation of f1t plus f2t. And number three, you need to define the amplitude and phase of ft, which is from question number 2. Okay, hopefully you understand the question is all about. Number one is to sketch the f1t and f2t in time domain, means that to answer question 1, you have to actually write the f1t and f2t in time domain equation. Then only you can sketch the spectrum. You can sketch the signal, sorry. And number 2, you need to add the f1t and f2t. And once you add them, then only you can find the trigonometric Fourier series for the ft. And number 3 will be related to number 2. Okay, so hopefully you understand the question is all about, yeah? Okay, so to answer question 1, what you have to do now is that you have to actually obtain the equations of f1t and f2t from their spectrum. Okay, so that should be the things that you have to do. First thing, yeah? The first thing that you have to do is that you have to write the f1t and f2t in terms of their time domain representation of time domain signal. Okay, so let's have a look on the solution for this example on how to represent the f1t and f2t in time domain. Okay, so this is the resketch of the functions, resketch of the spectrum for both f1t and f2t. So what I'm going to do now is that I'm going to write the f1t in time domain and f2t in time domain. So what we should get from the spectrum is that for f1t, it should be 30 cosine of 50t, because the frequency is 50, plus pi over 2. Okay, so this is the equations for f1t obtained from the spectrum. Whereas for the f2t, the equations will be negative 40, because the amplitude is negative, plus 40 cosine 50t plus pi, because the signals is located at 50 hertz of frequencies, yeah? Amplitude is 40 and the phase is pi. So that's why we have for f2t, the equations in time domain is given by this. Okay. All right. So hopefully you understand about this equation. So now we are going to use this f1t and f2t, which have been obtained. We're going to sketch this f1t and f2t in a time domain representation. So these are a few manipulation that I did for easier sketching. So I use a identity. So further on, I get that 30 cos 50t plus pi over 2 is equals to negative 30 sine 50t. And f2t, by further manipulation, we are supposed to get negative 40 minus 40 cosine of 50t. So you can work out for these equations, yeah? Okay, so by sketching this 30, negative 30 sine 50t, you're going to get this. Okay, so that should be the sketching for negative 30 sine of 50t, whereas for the f2t, the sketching for this will be obtained as shown here in this diagram, yeah? So you can prove this on your own, yeah? But if you spot any mistake that I did in this solution, please notify me later. Okay. Let's proceed further. So this is sketching of f1t and f2t, both of them in time domain, yeah? So number 2 is that you need to obtain the trigonometric Fourier series of ft, which is a summation of f1t and f2t. So what you have to do now is that you have to add the f1t and f2t. So the addition of those of both functions, we're going to have this. Okay, so we add them together. Negative 40 minus 40 cos of 50t minus 30 sine of 50t. Okay, so this is where I have to use a method, yeah, a way of combining the cosine and sine terms, having same frequencies component or frequencies value. So I'm supposed to get A, the new amplitude will be negative 40 squared plus negative 30 squared. This is the amplitude of the cos. This is the amplitude of the sine. You have 50 as the new amplitude. Whereas for the phase, you are supposed to get arctangent of negative amplitude of the sine over the amplitude of the cos. So which is 30 over 40. And the theta or the phase will be negative 36.87. So note that the theta, we need to remember that the arctangent will be the ratio between amplitude of the sine over the amplitude of the cos. So we have going to get the phase is negative 36.87 degrees. So from this calculation of the new amplitude and phase, we can now rewrite the ft as shown here, which is -40 plus 50 cos 50t minus 36.87. So this is the ft which shall be applied in yeah, this is your spectrum. Yeah, this is your Fourier series terms for the ft, which is a combination of f1t and f2t. And following this, we can know that the AC component for the ft, which is this one, yeah, this is a DC component. -40 is a DC component. AC component is a 50 cos 50t minus 36.87, in which the AC amplitude is 50 and the phase is -36.87. So this answered the examples that we have in the slides. Yeah. Okay. Any question for this example? Is there any questions? No? Okay, no questions. Let us proceed further. Sorry. Okay. Okay then. Okay. We are now going to proceed with the third part of Fourier series representation. So previously, for the first and the second type, the Fourier series is represented in terms of trigonometric terms, yeah, sine and cosine. But for the third terms, it is in a complex exponential form. Okay. We know that the cosine terms are given by this, sine is given by this, based on all relationship. So it can be shown that the Fourier series in complex exponential form can be written as shown here, where the Vt, this is the Fourier series, a summation of n from negative infinite to positive infinite of Cn exponential Jn omega naught t. So this is the equation of Fourier series in a complex exponential form, where Cn is the Fourier coefficient and is given by this integration terms. Yeah. Okay, you don't have to memorize this. It will be this. You can obtain this from the attachments given. Okay, and again, I want to stress to you one more time that you won't be tested on the integration to calculate the Fourier coefficients. Yeah. All right. So we know that up to now, for the third type of Fourier series representation, it is a complex exponential form and is given by this term, the summation of n from negative infinite, so positive infinite of Cn exponential Jn omega naught. Let's have a look at these examples, which will be tested on your understanding related to the complex exponential Fourier series. Yeah? Okay, so we are given these examples here, where we have two signals, xt and yt, are said to be added, and the addition of these will give us zt. Yeah, xt and yt, which will be added, will give us zt. In which xt and yt, both of them are identified as follows. Yt is given to be 3 sine 400 pi t plus 5, while the xt is given by -4 sine 200 pi t. Yeah. So we need to, number one, express this xt and yt graphically. Okay, means that you have to sketch xt and yt in time domain based on the given equations here. Number two, you have to construct the complex exponential Fourier series for zt, okay, which is the addition of xt and yt. And number three, we need to illustrate the double standard spectrum for the zt. Means that from what we've obtained from the second question just now, which is a complex exponential, we need to illustrate it in terms of double standard spectrum. Okay, yeah, hopefully you understand about this. So basically, number one is repetition, the same problems that we have faced before from previous example. We have to write the equations. We need to sketch the equation of xt and yt in terms of their representation graphically. Yeah, need to sketch the solid signals. Okay, so let's have a look at the solution for this. Okay, solution for like 7 here, we have this will be the signals. Yeah, this is the questions. We have xt and yt here. The zt is here. So yt is the signals and xt is here. So I believe that you can try this on your own. Okay, that initially when you have 3 sine 400 pi t, that should be a 3 sine 400 pi t. But when we have the amplitude shifting of 5, yeah, 5 is amplitude shifting. So all of them will be shifted upwards. Going to have the new signals, which will be now having a range from 2 to 8. Okay, so this is 3 sine 400 pi t plus 5. Whereas for the xt, where we have negative 4 sine 200 pi t, we have supposed to have a signal which should be looked like this. Yeah, so that should be your xt signal. So for the intersection on the x-axis, you can write this on your own. You can find this on your own. What should be the intersection for the signals at the horizontal axis? Yeah. And number 2 is that you need to add them together, which is the zt is a summation of xt and yt. So when we add them together, we have 3 sine 400 pi t plus 5 minus 4 sine 200 pi t. Yeah, so when we add them together, we have 5 plus these terms. Okay, and what we need to know is that we have to, what we did here is that we're using this identity, yeah, in which we're going to convert from sine to cosine. Okay, so we have from sine to cosine terms now. And since the question asks us to find the complex exponential part of process for zt, so what we did is that we are now transforming all the cos term into its complex exponential terms. Yeah, this is by using Euler's representation. So basically, you're going to have this representation in complex exponential. So you can try this on your own. Okay, and finally, you're going to have this is the final equation of zt in a complex exponential, 5 plus 3 over 2 exponential of g 400 pi t minus pi over 2 up to the 5th term here. So from this zt that you have obtained, you can straight away sketch the spectrum, double slit spectrum. Yeah, so we have 5, 2 as the amplitude at 200 pi and negative 200 pi, and also amplitude of 3 over 2 for frequencies of 400 pi and negative 400 pi. So the same things apply for the Z, for the phase, where for the phase we have at 200 pi, here the phase is pi over 2, negative 200 pi, the phase is negative pi over 2, at 400 pi positive, the phase is negative pi over 2, while for the negative 400 pi, the phase is positive pi over 2. Okay, so hopefully you understand now a conversion from trigonometric cosine to exponential Fourier series, and from exponential Fourier series you have then instructed to sketch the double slit spectrum for the signals. Yeah. Okay then. Is there any question? No. Okay. Is there any question there? No. Yeah. Okay. So I'm going to stop here. So we're going to continue these examples tomorrow. Okay, so as I mentioned in the Google Classroom entry, by right we're going to have a tutorial session tomorrow. Okay, tomorrow. So please be prepared for tutorial session. Yeah, those questions are actually related to related to chapter 1. Okay, so basically we want to test you on your understanding on chapter 1. Okay, so please be prepared. Yeah, because I don't have any solution for that. We're going to discuss the solutions in the Zoom platform. Okay. Okay. So for today's lecture, if you face any question still, you can straight away PM me for questions. Yeah. Right. And before we end the class today, I'm going to share again the QR code. QR code for the attendance. Yeah, please scan the QR code to ensure that you have already scanned for your attendance. Yeah. Okay then. Is there any questions before we end?
Doctor,
Yeah.
when exactly is the quiz?
When exactly is the quiz? Your question? When
Yes.
is it? Next
Yes.
week. Next week, but I'm not sure whether to have it on Sunday or Monday. You're not very sure.
But it's gonna be in the class. It's not gonna be
Yeah, yeah. In
separate.
the class.
Okay, okay.
In the class.
Yeah, okay. Thank you, doctor.
Welcome. So basically, you'll be tested your understanding on chapter 1. Yeah, on chapter 1.
Okay.
Okay then. Any more questions, guys? No? Okay, hopefully you gain something from today's lecture. Thank you very much for attending the lecture session. I'm going to give you the video link for today's lecture. Okay, so have a nice day ahead. Thank you very much. See you again tomorrow. Yeah. Thank you. Bye bye.